Kia ora and welcome back. In our last video we talked about permutations and we set up a nice notation for them using a kind of a two-row matrix. In this video we're going to introduce a new way of describing these things, which actually can be quite a lot more convenient to work with, and that's the notion of a cycle. Now the easiest way to show how this works is to just dive straight in with an example, and then we'll show how we can turn the matrix notation into this more convenient cycle notation. Right, so here's the permutation that we want to work with, and it's a permutation of 6 elements, so we're working with a permutation that's inside S6. Right, so the idea of cycles is that we take each element and we track it through the permutation as we apply it over and over again. So if I take my element 1, for example, if I apply the permutation alpha to 1, clearly it gets mapped onto 4. Right? If I go and then do the permutation again, where does 4 go? Well, looking over here, I can see that 4 gets mapped back to 1. So every time alpha is applied, I'm going to see that 1 bounces to 4, then back to 1 again, then back to 4, and so the 1 and 4 are just going to cycle around in position like this. Now we're going to track 2, because we're finished with 1 and 4. So I'm going to move on to my next one, which is 2, and see where it goes. If I apply alpha once, 2 gets mapped to 3. Again, 3 gets mapped to 5. Again, 5 gets mapped back to 2. So it looks like we have what we call a 3 cycle here. First time alpha gets applied, 2 gets mapped to 3. I apply alpha again. 3 gets mapped back to 5. I apply alpha again. 5 gets mapped back to 2. Okay, so this is called a 3 cycle. I guess you could call it a tricycle if you wanted to, but we tend to call it a 3 cycle. What's left? Well, we know what happens to 1, 2, 3, 4, and 5 now, because they all appear in the cycles that we've got. The only one left is 6, and 6 doesn't do a heck of a lot. Every time we apply alpha, it just gets mapped back onto itself. So, in terms of actually writing this down, we normally leave out the arrows. So cycle notation is basically just grouping those numbers together. So I'm going to group together 1 and 4, so omit arrows. Okay, with the understanding that 1 gets mapped to 4, 4 gets mapped back to 1. My next one, again, is following the numbers in the order they appear, following the arrows. 2 gets mapped to 3, 3 gets mapped to 5, 5 gets mapped to 2, so I close off the cycle. And then 6 gets mapped just to itself. Okay, so this thing here, this is like a product of cycles. This is called a 3 cycle. This is called a 1 cycle. And this is called a 2 cycle. Okay, so let's see what one of these things means in isolation, because I've got 3 different cycles sort of glued together here. We can think of a single cycle of a cycle, e.g. let's just write down 1, for example, 2 and 5, 2, 5, as a permutation that cycles 2 and 5 and fixes every other element. Okay, so every one of these cycles can be considered as a permutation in its own right. So what would 2, 5 look like? Again, we'll work in S6. So e.g. 2, 5, if I were to write 2, 5 out in full, it does nothing to 1. It maps 2 onto 5. It does nothing to 3. It does nothing to 4. It maps 5 onto 2, and it does nothing to 6. So in this way, we can consider 2, 5 to be a full permutation in its own right, and in fact, all 3 of the permutations in this row here can all be considered as 3 separate permutations like this, which have been multiplied together, and you'll see we get the same thing back. Okay, so that means we can multiply cycles. So just writing them down stuck together like I did before actually works as a multiplication as well. So we can multiply cycles in this way. So e.g., I'm going to take alpha to be 1, 3. Let's do a complicated one, or a relatively big one. So we're going to work in S8. 4, 5, 6. And does nothing to 8. And beta equals 1, 2, 3, 7. So it's got a 4 cycle, 6, 4, 8. And then 5. And I want to know what alpha beta is. Okay, so I just write the whole thing down as one big long expression. Every time there's cycles beside each other just counts as products in the sense of multiplying two permutations. Then I write down beta, 1, 2, 3, 7, 6, 4, 8, and then 5. Okay, so what we want to do is do the same procedure as we did when we wrote them out in matrix form, although writing all 7 of those things out in matrix form would be a bit of a nightmare. So we want to essentially express the same idea, and we want to track the different elements through from right to left and see where they end up after going through all of these cycles. So we'll start with 1, just like we did before, and I'm going to work from the right to the left and see what happens to 1 as it goes through each one of these cycles starting from the right. Okay, so my first one, 5. 5 is just nothing. Nothing happens. It's the identity. Okay, 1 gets left alone. So now I'm into this cycle here, and I'm still at 1. This one here also does not touch 1. 1 doesn't appear in it, so 1 is fixed. So I'm still at 1 after going through this second from the right. Now I move into this block here, and my 1 gets moved to 2. So now, after this one, it's keeping in my head, now I'm on 2. And I'm seeing what happens to 2 as I go further. Now I move to this block. 2 gets left alone by this permutation, so I can just continue on. 2 does not appear in this permutation here, only 4, 5, and 6 do, so I'm still on 2. I get to this one, 2 moves to 7. Okay, so after going through this permutation, I'm now at 7. Come to here, 7 gets left alone, so overall, 1 has been mapped to 7. Now I have to go right back to the right hand side and do exactly the same thing again. So 7 is not touched by this permutation. Moving across, 7 is not touched by this one either. Moving across, 7 gets cycled back round to 1 in this one, so now I'm at 1. I move across, 1 is left alone by here, I'm still at 1. 1 is left alone by here, I'm still at 1. 1 is left alone by this one, I'm still at 1. Finally, 1 gets mapped to 3, so my 7 overall has been mapped to 3. Rinse and repeat. 3 is not touched by this permutation. Now I'm seeing where 3 goes. 3 is not touched by this one, still at 3. 3 gets mapped to 7. Now I'm on 7. 7 is not touched, still on 7. 7 is not touched, still on 7. 7 is mapped to 2. Now I'm on 2. 2 is not touched by this one, so I stay at 2. Okay, continuing. Now we need to see what happens to 2. Start from the right. You can kind of see how this is working now. Perhaps you're getting ahead of me. 2, not touched. Still on 2. Still on 2. Now at 3. Still on 3. Still on 3. Still on 3. 3 gets mapped back to 1. Aha, but 1 is the start of our cycle, so now I can close this off because my 2 overall gets mapped to 1, and so I have my first cycle. Okay, so part of this product is a cycle 1732. Now let's go to the next thing that we haven't yet dealt with, which is 4. And we'll track 4 through. So now I'm just going to do it a little bit faster. Still at 4. 4 goes to 8. 8, 8, 8, 8, 8. Overall, 4 goes to 8. You can see that once you've done this a few times, it actually is quite fast. It feels really intensive when I'm sort of saying it all in great detail at the start. But once we get used to doing this, it's actually quite straightforward. So now I'm at 8, so I'm going to track 8 through. So not touched goes to 6, 6, 6, 6 goes to 4, 4, 4. So 8 overall goes to 4. We can close this cycle off. Now, what have we not yet seen? 1, 2, 3, 4. It looks like 5 is next. Okay, 5 left alone, 5, 5, 5, 5 goes to 6, 6, 6, 5 and 6, okay? Now we're going to track 6. 6 is left alone, 6 goes to 4, and this one, 4 is left alone, 4 is left alone, 4 goes to 5, and this one, 5 is left alone, 5 is left alone, so 5 and 6 close off. And you can see I've now put together my product as a product of cycles. Okay, so this always works. Right, so a couple of notes. We usually don't even write one cycles. Because they don't do anything, we just usually leave them out. Okay, except if we need to identify what the identity is, except the identity. Epsilon, which we usually just write as a one cycle of 1. But in fact, any one cycle is the identity. It's all the same thing, because a one cycle doesn't actually move any elements at all. So usually, if instead of writing down, say, for alpha here, I would not normally write down the 8. I'd normally just leave that off altogether, because it doesn't actually add anything to the permutation. All right, what else can I say? Inverses of cycles are the same cycle in reverse. E.g., 1, 3, 4, 2. Inverse, you can just write it down as 2, 4, 3, 1. Okay, the last note, there are different ways of writing the same cycle. In particular, we should be aware of these because it can be a little bit of a trap sometimes. E.g., again, I'll start with the same one, 1, 3, 4, 2. Remember, that's just, if we're thinking of back to our picture over here, we're just thinking of a circle with those things in that order in it. So it doesn't actually matter where we start the circle off. So that's the same as writing 3, 4, 2, 1, which is also the same as writing 4, 2, 1, 3, which is also the same as writing 2, 1, 3, 4. So don't get tripped up by this. There are multiple ways of writing the same cycle. In each one of these 4, the elements appear in the same order, so that's all good. But we need to be aware that it doesn't matter which one we start at. So for example, if we're trying to count cycles, we need to make sure we account for the fact that we can write them in different ways. Now, we've got some theory to go with this, and I'm not going to prove these next two theorems because the techniques involved in the proof are pretty much exactly the same techniques that we used in our constructions earlier in the video. So I will leave you to read the proofs in Galilean for yourselves, but essentially we have kind of proven them with our examples by construction already. So the first one says that every permutation of a finite set can be written as a cycle or as a product of disjoint cycles. That means cycles with no elements in common. Let's just write a little note there. Cycles, no elements in common. Okay, so that's the one. Remember we did that example when we wrote down at the beginning of the video, we had that permutation 1, 2, 3, 4, 5, 6, and then we had 4, 3, 5, 1, 2, 6. And the idea was that we just started with 1 and we tracked it. So 1 went to 4, 4 went to 1, we closed it off. Then we found 2, 2 went to 3, then 3 went to 5, and then 5 went back to 2, so we closed that off. Then 6 was by itself, and you can see what we got here. This process automatically gives us a cycle, either a single cycle if everything was involved, or a product of disjoint cycles. We never get any two numbers appearing in the same cycle, just exactly by the way we constructed it. So the proof, if you follow along in Galilean, essentially formalizes that process and uses letters to do the same thing as we just did. Okay, so for our next theorem, is theorem 5.2, and it says that disjoint cycles commute. Now again, we've kind of done this already, in that if I take the cycle 4, 5, 6 times 1, 2, 3, automatically I can see that if I'm trying to figure out where 1 goes, for example, it's only touched by the right-hand permutation. As I'm trying to compose these right to left, 1 goes to 2, 2, none of the things in this right-hand one, in fact, appear in the left-hand one. So it doesn't matter whether I do it before or after 4, 5, 6. So it's a useful thing to note down explicitly, though, is that when we have disjoint cycles in our permutation as a product, we can always commute them. And again, I'll refer you to Galleon for the proof of this, because it's not hugely complicated and it's kind of obscures what we're actually trying to talk about here. Worth noting, so disjoint cycles always commute, and the previous theorem, every permutation can be written in disjoint cycle form. Okay. The next one that we want to look at is to look at the order of cycles, and this one we will prove. And the theorem goes a little something like this. The order of a permutation is basically, when you write it down in disjoint cycle form, so let's just put some parentheses around here so it's clear, it's the LCM of the lengths of the cycles. So if we were to look at this example up here that we had, the length of the first cycle is 2, the length of the second cycle is 3, and so the theorem is saying that the order here should be the lowest common multiple of both 2 and 3, which has order of 6. So order of thing would equal 6. All right, so we need to prove this because this one is a bit more of a bigger statement than the previous two. Okay, so proof. Let's just look at a single cycle first. A cycle of length n has order what? Well, if I look at 1, 2, 3, again, I'm just going to scribble in this space up here. 1, 2, 3, if I apply it once, so 1, 2, 3 squared equals 2, 3, 1. 1, 2, 3 cubed, if I multiply another one again, shift it across one more time, and I will get a mistake. Let's back up. Sorry about that. If I were to square 1, 2, 3, let's actually not rush and do it in detail. So I'm going to start with 1, 2, 3. 1, 2, 3 to the power of 1 is just 1, 2, 3. 1, 2, 3 squared. This time, 1 is going to get mapped to 2. 2 is going to get mapped to 3. So this one actually takes 1 to 3 and takes 3 to 2, and that's what I'll get. And then 1, 2, 3 cubed, now my 1 is going to cycle around 3 times, and actually I get the identity if I take it to the power of 3. So a cycle of length n has order n. So hopefully we can convince ourselves that that's true. Okay, so now what we're going to do is we're going to take two disjoint cycles and define their LCM. So let alpha and beta be disjoint cycles of length m and n. And I'm also going to want to refer to the LCM, and I'll let k be the LCM of m and n. Okay, so let's see if we can prove that the order of alpha times beta is equal to the LCM of m and n. All right, so theorem 4.1 from a previous video basically says that alpha to the k and beta to the k are both the identity. We use epsilon for permutations, as k is a multiple of order of alpha and order of beta. Okay, so remember, if you take the order of, so alpha has order m, so taking alpha to the power of m gives me the identity. K is a multiple of m, so it's just doing that some number of times, so it's always going to be the identity. Same logic applies to beta. Okay, so if I take alpha beta to the k, alpha beta to the k is equal to alpha to the k, beta to the k, because alpha and beta are disjoint. Let's actually make an explicit note of this because it doesn't automatically hold. Disjoint cycles commute. Because they are disjoint, I can group all the alphas together and all the betas together. So therefore, alpha beta to the k is equal to the identity. So hence, t, which I'm going to define to be the order of alpha beta, divides k. Make sense? Remember, if I have a power of an element equaling the identity, then that power is a multiple of the order of the element. So here, the order is t. K gives us the identity, alpha beta to the k. Therefore, t must divide k. K must be a multiple of t. Okay, so that's interesting. If I have, therefore, if I now take alpha beta to the power of t, just kind of messing around with what things I can do with what I've defined so far and see if this gets me anywhere. Alpha beta to the t has to equal the identity, but it's also equal to alpha to the t, beta to the t, which has to equal the identity, because t is the order of alpha beta. And hence, if I rearrange this expression, I'm going to put all the alphas on one side and all the betas on the other side. Okay, here's the little trick here. Because alpha and beta are disjoint, on the left I have power of alpha, and on the right I have a power of beta. Now, because they contain no symbols in common, the only way that these things can be the same is if, in fact, they're both equal to the identity. Since alpha and beta are disjoint, and powers don't introduce new symbols. If I take powers of cycles, I don't get new symbols introduced. I get alpha to the t is equal to beta to the negative t, which also equals beta to the t, which is equal to the identity. Hence, now I can apply the same logic I applied before. I have something to the power of t is the identity, and we know the orders of these things are m and n. M divides t, and n divides t. And what can we then say? Well, therefore, if m and n both divide t, then t is a common multiple of m and n. But hang on, right at the start we said if we've got a common multiple that the power is equal to the identity. So the lowest of these is k, and therefore we're saying that any common multiple gives us t divides k and k divides t, and therefore the order t equals k, which is what we require. How'd that work again? Well, t divides k, and t is a common multiple of m and n, therefore the only thing possible is that t equals k. Okay, so what that means is we can find now the order of a permutation by just figuring out the LCM of all of the length of the cycles. The key point to not forget when we're actually practically doing this is that it has to be in disjoint cycle form first, otherwise it won't work. So we'll finish with an example where we calculate the number of elements in S7, for example, of order 3, and show how we can use what we know about orders being the LCM of the length and disjoint cycles to help us understand that. Okay, S7, these are permutations of 7 objects, and we want to count the number of objects in S7 that have order 3. So that means that if I write an object in disjoint cycle form, the LCM of the cycle lengths must be 3. So LCM of cycle lengths must be 3. So there aren't actually that many possibilities. We could have a cycle of length 3. So I'm just going to use underline 3, kind of to indicate a cycle of length 3. The only other possibilities here, there are quite a few different cycles of length 3 that we can construct, of course. We could have a cycle of length 3 glued onto another cycle of length 3. Can you think of any other possible disjoint cycle structures that will have an LCM of their lengths being 3? There aren't really any. As soon as I say introduce a 2 cycle, then I'm at minimum order 6. So actually I've only got these 2 possibilities for cycles that have LCM of their lengths being 3. Alright, so question, how many cycles of length 3, how many of these are there? Well, these look like A1, A2, A3, and then if everything else gets left fixed. So we could specify A4 was fixed, A5 was fixed, etc. But because they're just all those single cycles are just the INC, we leave them alone. Well, we know that we have 7 choices for A1. We have 6 choices for A2, and once we've chosen those 2, there are 5 choices remaining for A3. So there are 7 times 6 times 5 possible 3 cycles that we can come up with in S7. But wait, that's not quite right. Remember what we said before? Actually, there are 3 different ways of writing down each of these 3 cycles, depending on which one we start with. So of this sort, there are 7 times 6 times 5 divided by 3 possible ways of writing down a 3 cycle like this. So that number is, in fact, 70. Okay, 7 times 5 times 2 is 70. Now we want to count how many different ways there are of building a 3 cycle times a 3 cycle. So that will look like A1, A2, A3, and then there'll be A4, A5, A6. So we can go through again, do the same exercise. Let's build the first one first. We've done that already. So there are 7 times 6 times 5 divided by 3 possible choices here. And for each of those choices, there are 4 remaining for A4, 3 remaining for A2, times 2 remaining for A6. And again, we've got to divide by 3 because these cycles could start in each of 3 possible ways. Okay, are we done? Is that our final answer? There's one other little trap here. Because they're disjoint, they commute. So actually, if we just leave it like this, we're double counting, because if I were to take, for example, 1, 2, 3 times 4, 5, 6, that's the same as 4, 5, 6 times 1, 2, 3, yet we're currently counting them as being different. So everything in that second term has been double counted, so we have to multiply by a half out the front. So overall, we're going to have 70 of these ones, and then of the other type, we're going to have 1/2 times 70 times 8, right, which is 280, so equals overall 350 possible elements in S7 that have order 3. And we should probably have done a slightly simpler example just to practice using our LCM. So what is the order of 1, 2, 3, 4, 5, 6, 7? Well, that's a cycle of length 4, that's a cycle of length 3, so the LCM of 4 and 3 is just 12. So the order of this one here is equal to 12. What about the LC? What about one more example to finish off, just to have an LCM that's not actually the multiple? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we're in, for example, S10. That cycle has length 6. That cycle has length 4. And the lowest common multiple of 6 and 4 is 12. So that equals 12. Okay, so worth practicing some other examples like this one we just did in S7, where we count the number of elements in a symmetric group of a certain order, because it's quite a good sort of thoughtful exercise, and it sort of brings to bear some of the previous theorems that we've talked about, especially the one about commuting and that factor of a half. That's quite an easy trap to make by accident. Yeah, so I'll leave it at that for this video. It's got long enough already. Next time we'll come back and look at turning cycles into 2 cycles. So that's all for now. Ka kite anō, we'll see you next time.